Hello, everyone. So today I'm going to present a recent work published last year. Basically, we used the foreground and background galaxy pairs to trace the structure and kinematics circumgalactic neutral hydrogen around redshift 2. A lot of authors on this paper are also in this workshop. And if you're interested, feel free to check out our paper. Here's the archive link. So what we did in this paper, we constructed the largest galaxy pair sample at redshift 2. We basically used the Keck Baryonic Structure Survey, 20 years of data, where this survey contains about 3,000 spectroscopically confirmed star-forming galaxies around redshift 2. By matching these galaxies into non-interacting galaxy pairs, we were able to basically match over 200,000 galaxy pairs. And the goal here really is that we want to increase the spatial resolution of the Lyman-alpha absorption features. That's because galaxies' sightlines are more common than quasar, was commonly used as in quasar sightlines. So with these 200,000 galaxy pairs, if you treat all of the foreground galaxies as a huge statistical sample, you're basically imaging with such a dense sampling, you're basically taking an eye view data of the Lyman-alpha absorption in the CGM. So we basically stacked these spectrum at the redshift of foreground galaxies. And you can see that, these are stacked spectrum, of course. So you can see that, not surprisingly, as you increase the impact parameter or the distance to the central galaxy, the absorption signal of Lyman-alpha absorption decreases. That's not surprising. But what's actually very intriguing from our result is that the line shape, the line profile also changes very significantly. So this map, the y-axis is the line sight velocity, x-axis is the distance again. And the color coding here is basically how strong the absorption is. And so each one column of the pixels in this plot is just one spectrum on the left. So you can see that this very unique Lyman-alpha absorption feature around redshift 2 star-forming galaxies. So we want to understand what's happening. We first compared it to the fire simulation, in which you can see this clear inflow and outflows going in and out as the galaxy formation is going on. So we projected this into this plane that we can actually observe. So the y-axis, again, is the line of sight velocity, x-axis is the impact parameter. So you can see during this process, the inflows being funneled into the center galaxy and then outflows being thrown out at higher velocities. So we compared it. So the comparison between the fire simulation and observation are qualitatively in agreement. The contours are from our observation, and the color is the fire simulation. We constructed a model to further quantify and constrain what's going on. This toy model contains only the radial inflow and outflow, and the model is basically for the outflow is ballistic, and for the inflow it's a constant inflow velocity offset by the Hubble expansion. So we fit it to our observation, and you can see that the model is doing a relatively good job here. And we can also further constrain which part in this map is dominated by outflow, which part is dominated by inflow. But of course, the model is oversimplified, and we acknowledge that there are other families of models that may work. For example, if you substitute the outflow velocity from ballistic to power law outflow velocity, you can see it's still doing a fairly good job. However, we want to acknowledge that the important part is that if we only use single inflow and outflow models, the model basically fails to fit whatever the observation is. So that's a pretty strong signal that by increasing the spatial resolution using galaxy pairs, we are able to say that both the inflow and outflow exist in this map. So here's a brief summary, and I'll stop here.